Welcome to Module 2 of the AASHTO training course on the principles and application of the BCT, which is the back calculation tool for rehabilitation design using the PMED software course. Module 2 will focus on the fundamentals of falling weight deflectometer testing and back calculation of elastic layer moduli. Going back to the course roadmap that was presented in Module 1, this portion or Session 1 of Module 2 is on deflection testing. In this session, we will overview the fundamentals about deflection testing, especially focusing on the falling weight deflectometer, because FWD deflection data is input to the BCT. There are 5 learning outcomes for Session 1 of this module. The first is to understand why deflection testing is important in the context of pavement rehabilitation and performance. The second is to list the deflection testing methods that have been used in the past and the deflection testing devices providing data applicable to the BCT. The third is to identify different components and variables of the FWD deflection testing devices and procedures. The fourth is to explain the file structure indices and list the reasons for segregating the deflection data for use in the BCT. And finally, the fifth outcome is to define the FWD data and its output that are required for use in the BCT to back calculate elastic layer moduli. There are 5 major topics within Session 1 of Module 2. The first is a brief history and overview of deflection testing. The second topic is standardization FWD testing procedures and test protocols. The third is a focus on the fundamentals of deflection testing with outputs associated with deflection testing. The fourth is how FWD data is used in the BCT software for rehabilitation design. And finally, the fifth is a topic on setting up the deflection files to be used in back calculation. So, let's first discuss and overview the principle of deflection basin testing and why deflection testing is important. The basic principle of deflection basin testing is to apply a known load to the pavement surface. The picture on the right shows an impact load applied to the pavement surface. That load results in the pavement deflecting, and the deflections are an indication of how stiff or strong the pavement layers and subgrade are. The schematic of the deflection basin shows the deflected pavement surface, obviously in an exaggerated form. Measuring the deflections at different distances from the applied load defines the deflection basin. An analysis of the deflection basin tells us where the stiff or soft layers are located beneath the surface. A couple of reasons why deflection testing became very popular for pavement engineering. Pavement deflection testing is a quick and easy way to assess the structural condition of an in-service pavement. Deflection testing is also completed in a non-destructive manner. In other words, we are not damaging the pavement or removing material to collect the deflections or pavement responses. Over the years, a variety of deflection testing equipment has been used for this purpose, from simple beam-like devices affixed with mechanical dial gauges to more sophisticated equipment using laser-based technology. Nevertheless, all pavement deflection testing equipment operates in a similar manner. A known load is applied to the pavement, and the resulting maximum surface deflection, or an array of surface deflections located at a fixed distance from the load, known as the deflection basin, are measured. You can see the deflected surface after the load is applied to the original surface. The shape of the deflected surface is known as the deflection basin. 2 test methods have been standardized for collecting and analyzing deflection data. The first one is AASHTO T256, which is a standardized method for measuring and collecting the pavement responses or deflection basin. And ASTM D5858 is the standard guide for estimating the equivalent elastic layer moduli of pavement materials using elastic layer theory. Many other test methods and standard practices are available. In fact, most state agencies and organizations have their own standardized methods for collecting and interpreting deflection data. These are simply examples of 2 standardized methods at the national level. In general, there are 3 primary methods for conducting deflection testing that are listed on this visual aid: static loading, steady-state loading, and impact loading. The most common device used for the static loading method is referred to as the Binkelman beam. The Binkelman beam device is based on level arm principles, where the tip of the device is placed between the dual tires of a single axle loaded to 80 kilonewtons, which is 18,000 pounds, and the tires are inflated to 480 to 550 kilopascals, which is 70 to 80 pounds per square inch. For steady-state loading, the Deflection trailer is one of the devices used. For steady-state loading, a non-changing vibration using a dynamic force generator is applied to the pavement surface, and deflections are measured using the velocity transducers. The Deflection trailer shown in the center picture is a very well-known steady-state loading device for deflection testing, but a device referred to as a road rater has also been used. Impact loading has become the most common deflection testing method used now. The falling weight deflectometer is the device used by most agencies when measuring pavement response from impact loads. In summary, a weight at the known height is released to apply an impact load to the pavement surface. The load is measured by a load transducer, and the deflections are measured at known distances from the impact load. The BCT uses data from FWD testing or impact loading, so the FWD will be the focus of the remaining sessions and modules of this training course. The falling weight deflectometer deflection testing devices use impulse or impact loading by dropping weights at various heights to apply the impulse load ranging from 6.7 to 120 kilonewtons, which is 1,500 to 27,000 pounds, to the pavement surface. The drop height of the loads is increased to impose higher loads on the pavement surface. In general, 3 drop heights are used to determine how the load responses of the pavement change with higher loads. Deflection basin created by the impact load is measured by 7 to 12 sensors or geophones that are located at specific locations from the loading plate as shown in this schematic. 9 sensors are typically used to measure deflection basin. The long-term pavement performance, referred to as LTPP program, use the FWD device to test all sections within that program. So, the majority of state and other agencies in North America use the FWD device for deflection testing. The spacing or location of the sensors is dependent on the type of pavement structure, but the locations used in the LTPP program has standardized the sensor locations for most pavement. A few agencies use a constant spacing of 12 inches between the sensors, while most agencies use the LTPP spacing. The common location of the sensors is 0, which is typically under the loading plate, 8 inches, 12 inches, 18 inches, 24 inches, 36 inches, 48 inches, 60 inches, and 72 inches. The location of the sensor was determined to gather the best information to derive the elastic modulus, or stiffness of each layer below the surface. In other words, the locations were not selected at random. They were strategically located to collect information on the deflection basin and matching that basin to a calculated deflection basin. As noted in the earlier slides, guidelines have been prepared for measuring deflections. The 3 listed on this slide were prepared through the LTPP program. Most states and other agencies have prepared their own guidelines, which can deviate slightly from the more national guidelines. The next portion of this session includes a short video showing the operation of the FWD in collecting the load and deflection data for use in pavement evaluation and rehabilitation design.
From various heights, causing various loads to be applied on the pavement. So we're doing roughly 3 drops and mobilizing each time. Down. Second drop, right up, third.
Some of the earlier slides identified the important variables for the FWD deflection testing. We will focus more on those variables and how they may change for different uses, such as forensic investigations versus rehabilitation design. Remember, fixed guidelines need to be followed during the FWD testing, which are related to the physical testing equipment configuration, such as sensor locations and load levels, as well as the type and location of deflection data. 4 variables are listed on this slide, and one will be discussed on the following slide, testing location. First, let's start with the number of sensors and sensor location. The LTPP program's 9-sensor configuration is recommended for most routine roadway testing, but other configurations are also acceptable. An advantage of using 9+ sensors is the ability to perform PCC joint or crack load transfer efficiency, which is LTE testing without relocating a sensor from the testing configuration. As we stated in a previous slide, the number of sensors was based on the extensive testing of all sections within the LTPP program, as well as over 2,500 roadway sections spread across North America. The spacing or location of the sensors was mentioned in a previous slide within this session, but we will repeat it because it's so important relative to the back calculation of elastic layer moduli. The spacing or sensor location is dependent on the type of pavement structure, but the locations used in the LTPP program have standardized the sensor locations for most pavements. A few agencies use a constant spacing of 12 inches between the sensors, while most agencies use the LTPP spacing. The common location of the sensor is 0, which is typically under the loading plate, and then comes 8 inches, 12 inches, 18 inches, 24 inches, 48 inches, 60 inches, and 72 inches. Next is the load level and number of drops. First, the number of drops from the same drop height, which is 1 load level. The LTPP program recommends multiple drops from the same drop height, or at least 2, but preferably 3 at different load levels for both asphalt or flexible and rigid or PCC pavement from a repeatability standpoint. ASTM D4964, which is Standard Test Method for Deflections with a Falling Weight Type Impulse Load Device, recommends that at least 2 drops should be performed, whereas the American Association of State Highway and Transportation Officials, which is AASHTO T256, Standard Method of Tests for Pavement Deflection Measurements, and ASTM D4695, which is Standard Guide for General Pavement Deflection Measurements, suggest 1 or more drops at any load level will suffice. LTPP also suggests at least 3 drop heights or load levels should be used. Remember, as the drop height increases, the load level increases. Many agencies, however, use 1 drop height for rehabilitation design. 1 drop height is considered acceptable for rehabilitation design needs. The reason is for productivity of testing. The fewer drop heights, the quicker the testing can be completed. For forensic and research investigations, the number of drop heights needs to be at least 3. Next, temperature measurements during FWD testing. Temperatures are important because they do impact the deflections, especially for thicker asphalt pavements. As the temperature increases, the asphalt modulus decreases, so the deflection basin increases. For rigid pavement, temperatures can also have a large impact on the deflection basin because of the curling and warping of the PCC slabs. Within the LTPP program, pavement temperatures were measured, but for routine pavement evaluation and revelation design, pavement temperatures are rarely measured because it takes a lot of time and effort to measure pavement temperature. As a minimum, however, the air and pavement surface temperatures are recorded. These 2 variables can then be used to calculate the pavement temperature for use in rehabilitation design. Finally, the testing increment. More universal guidance is offered by the MEPDG, AASHTO T256, and ASTM D4695, which suggests basin test spacing of 30 to 150 meters, which is 100 to 500 feet for project-level investigations. Network-level testing is commonly performed to obtain a general indication of the load-carrying capacity of the pavement structure as a means of identifying and prioritizing projects for maintenance and rehabilitation. Network-level testing locations are generally 500 feet or more. For design, 500 or less feet really needs to be used to get project-level data. The testing increment is highly variable, but 100 to 500-foot intervals are typically used along a lane for rehabilitation design. The location along the lane is staggered from the adjacent lane to get the maximum coverage of the pavement and subgrade support conditions or strength. The testing increment is up to the designer, and the increment can vary along the project depending on the variability of the site conditions and surface distresses. The final FWD deflection basin testing variable discussed is the testing location. By location, we are referring to what type of location is the FWD measuring the deflections. As an example, wheel path, non-wheel path, across a transverse joint or crack, edge lane, and/or corner measurements. Deflection basin tests are used for back-calculating pavement layer parameters and are generally taken at non-distressed areas for flexible pavement and at midpoint, which is also non-distressed locations, for rigid pavement. However, the MEPDG recommends that FWD testing should be conducted in distressed asphalt areas as well to determine the damaged modulus. Deflection basin tests are typically performed in the center or mid-slab of rigid pavement and along the center of the lane or outside wheel path on asphalt and semi-rigid pavements. Tests across transverse joint of jointed plain concrete pavement and across transverse cracks in all types of pavement are measured and used in rehabilitation design. The deflections across the transverse joints and cracks should not be used in back-calculating elastic layer moduli, but are used to estimate the load transfer efficiency across the discontinuity. The back calculation engine included in the BCT is based on elastic layer theory, and the simulation of cracks and joints is not possible. For asphalt and semi-rigid pavement, the testing locations are along the center of the lane or in the outside wheel path for safety purposes, locating the FWD device as far as possible from the adjacent lanes with traffic. The use of FWD deflection basin testing to collect response data of the pavement structure and subgrade for rehabilitation design can be grouped into 6 major areas. The first area of use is to determine or estimate the structural adequacy of an existing pavement. Structural adequacy refers to the in-place damage of the bound pavement layers. Knowing the in-place damages allows the designer to determine the pavement's capability to handle future traffic loadings. The second area is to use deflection basins or structural responses of the existing pavement structure to back-calculate the elastic layer moduli for structural layers and subgrade for asphalt or flexible and rigid pavements. The in-place elastic moduli are used to determine the conditions of the structural layers. The third area is to segregate the project into areas with similar pavement responses or deflections. This area is used to strategically locate borings and cores to confirm the layers, condition of the layers, and subsurface soil strata. The fourth area is to estimate the load transfer efficiency of transverse joints and/or cracks in the existing pavement. Load transfer efficiency has an important impact on the occurrence of cracks in the asphalt overlays and long-term condition of the joints in a jointed concrete overlay through its rehabilitation life. The fifth area is specific to rigid pavements by estimating whether there is a loss of support or voids beneath the PCC slab. The sixth area is more specific to asphalt pavement by estimating the occurrence of disintegration, like moisture damage and other mixture deficiencies in asphalt layers. The use of deflection basin tests for use in rehabilitation design is divided into 2 groups of uses. The first is direct use of deflection basins in the BCT, and the other is an indirect use of deflection basins not directly required in the BCT. Let's briefly review the uses within each group. First, the use group for direct use in the BCT, which has been referred to in some of the previous slides. This listing is specific to the direct and indirect use. Deflection basins are used directly in the BCT to segment the project into sections with similar structural responses. This can be used to strategically locate borings and cores. Back calculate the elastic layer moduli of the pavement structural layers and subgrade. Estimate the load transfer of transverse cracks and/or joints. Locate areas along the project where a loss of support occurred, or potential voids, or locate layers that exhibit material disintegration. The indirect use of deflection basins for rehabilitation design, but not specific to the BCT, is to identify or determine the variability in structural response along the project length. Identify areas with excessive deflection so soft spots can be selected for pre-overlay repairs. And identify layer defects or disintegration for pre-overlay repairs and/or to select an optimum rehabilitation strategy. Deflections are also used to estimate load transfer efficiency of joints and cracks in rigid pavements and transverse cracks in asphalt pavements. Load transfer efficiency is important to predict reflection cracks in asphalt overlays. Load transfer efficiency is a critical input to the PMED software. The BCT includes a feature to calculate the load transfer efficiency. Deflection basins are also used to detect if there are any voids or a loss of support under PCC slabs and estimate whether there could be severe moisture damage or mixture disintegration in the asphalt layer to determine the type of repair strategy needed for the project. This visual aid designates the FWD data needed for back calculation and proper determination of the back calculation values. The date and time of deflection testing is required, the drop number and drop heights or loads. The FWD deflection testing variables include load plate diameter, load levels or drop height, sensor spacing or location, test points or location along the project. This will be discussed in more detail in the next slide. Maximum deflection measured by each sensor for each load or drop height. And finally, pavement or air and surface temperature at the time of FWD testing. As part of the data interpretation, this slide lists the file indices used to determine the test locations along the project. These are the lane and direction designation index, the test type designation to determine or designate the wheel path or non-wheel path for asphalt surface pavements or mid-slab location of jointed plate concrete pavements, corner and/or edge measurements for rigid pavements, and the load transfer efficiency designation for estimating the load transfer efficiency of JPCP transverse joints, JPCP transverse cracks, and transverse cracks in asphalt or semi-rigid pavements. This ends Module 2, Session 1, which was focused on FWD testing. The next module of the training course, Sequencing, is Session 2 within Module 2, and that will be on the back calculation structure simulation and layer thickness determination.